The idea that characters can fly from planet to planet or star to star, defying current science and technology, is central to science fiction. Although some of these ideas predated the space age, after the 1950s, fictional depictions of space travel needed to suggest conceivable ways to cross interstellar distances to seem plausible. Some authors suggested faster-than-light drives, jump drives, wormholes, and black holes. But would it be possible for spaceships to travel faster than the speed of light? In this video, we're going to take a closer look into what the physicists are saying on this subject. In Isaac Asimov's Foundation series, humanity can travel from planet to planet, star to star, or across the universe using jump drives. Some characters, like the astronauts in the movies Interstellar and Thor, use wormholes to travel between solar systems in seconds. Another approach, familiar to Star Trek fans, is warp drive technology. Warp drives are theoretically possible, if still far-fetched technology. According to physicist Albert Einstein's general theory of relativity, on which much of modern physics is based, nothing in the universe can travel faster than light. The theory states that as matter approaches the speed of light, that matter's mass becomes infinite. That means the speed of light functions as a speed limit on the whole universe. The speed of light is so immutable that, according to the U.S. National Institute of Standards and Technology, it is used to define international standard measurements like the meter and, by extension, the mile, the foot, and the inch. Einstein's theory also describes how mass and energy warp spacetime. Hefty objects like stars and black holes curve spacetime around them. This curvature is what you feel as gravity, and why many spacefaring heroes worry about getting stuck in or falling into a gravity well. Light traveling through a vacuum moves at exactly 299,792,458 meters per second. Even traveling at this dizzying speed, it would still take us 4 years to arrive at Proxima Centauri, the nearest star to the Sun. This speed limit makes it unlikely that humans will ever be able to send spacecraft to explore beyond our local area of the Milky Way. But that hasn't stopped scientists and science fiction writers alike from spending time contemplating faster-than-light travel. New stories, new inventions, and new realms of physics are constantly being investigated. In 1994, Miguel Alcubierre, a Mexican theoretical physicist, showed that compressing spacetime in front of the spaceship while expanding it behind was mathematically possible within the laws of general relativity. So, if you imagine the distance between 2 points is 10 meters, you are standing at point A and can travel 1 meter per second, it would take 10 seconds to get to point B. However, let's say you could somehow compress the space between you and point B so that the interval is now just 1 meter. Then, moving through spacetime at your maximum speed of 1 meter per second, you would be able to reach point B in about 1 second. In theory, this approach does not contradict the laws of relativity since you are not moving faster than light in the space around you. Alcubierre showed that the warp drive from Star Trek was in fact theoretically possible. The concept of warp drive is to say, let's take our spaceship, build a bubble of space-time around it, and then we will have that propel us faster than the speed of light. The bubble surrounding the ship is an area of space-time that is compressed in front of the spaceship and expanded behind it. As with gravity, you could create this distortion using a large amount of mass. Alternatively, thanks to Einstein's E equals mc squared, you could equally use a huge amount of energy. Unfortunately, actually creating a warp drive is even harder than it sounds. You have to have an extremely large amount of energy. In fact, to have the deformation for this kind of thing to work, you would need a lot more energy than the Sun or the galaxy. Also, bearing in mind, it is negative energy. Negative energy is not something that we can currently create, certainly not in the quantities needed to power a warp drive. So, what is negative energy? One way to think about it is to consider a particle with negative mass. These particles would react to gravity in the exact opposite way to particles of positive mass. Instead of being pulled towards a planet or star, they would be thrown away. If we had some sort of component like that where we had a negative mass, whatever is keeping that mass together would be that negative energy. Alcubierre estimated that a warp drive with a 100-meter bubble would require the mass of the entire visible universe. In 1999, physicist Chris Vandenbroek showed that expanding the volume inside the bubble but keeping the surface area constant would reduce the energy requirements significantly to just about the mass of the Sun. A significant improvement, but still far beyond all practical possibilities. Two recent papers, one by Alexei Bobrik and Gianna Martire and another by Eric Lentz, provide solutions that seem to bring warp drives closer to reality. They show that any warp drive must be a shell of material in a constant state of motion, enclosing a flat region of spacetime. The energy of the shell modifies the properties of the spacetime region inside it. This might not sound like much of a discovery, but until now it was unclear what warp drives might be, physically speaking. Their work tells us that a warp drive is, somewhat surprisingly, like a car. A car is also a shell of energy in the form of matter that encloses a flat region of spacetime. The difference is that getting inside a car does not make you age faster. That, however, is the kind of thing a warp drive might do. Using their simple description, Bobrik and Martire demonstrate a method for using Einstein's general relativity equations to find spacetimes that allow for arrangements of matter and energy that would act as warp bubbles. This gives us a mathematical key for finding and classifying warp technologies. Their work also manages to address one of the core problems for warp drives: negative energy. Bobrik and Martire show a warp drive could be made from positive energy, for example, normal energy, or from a mixture of negative and positive energy. That said, the energy requirements would still be immense. If these two physicists are right, then a warp drive is just like any other object in motion. It would be subject to the universal speed limit enforced by general relativity after all, and it would need some kind of conventional propulsion system to make it accelerate. Many kinds of warp drive can only modify the spacetime inside in a certain way, by slowing down the clock of the passenger in exactly the way that makes a trip into deep space a problem. Bobrik and Martire do show that some warp drives could travel faster than light, but only if they are created already traveling at that speed. Independently, Eric Lentz also proposed a solution that does not require negative energy. He used a different geometric approach to solve the equations of general relativity, and by doing so, he found that a warp drive would not need to use negative energy. Lentz proposes that conventional energy sources could be capable of arranging the structure of spacetime in the form of a soliton, a robust singular wave. The soliton would act like a warp bubble. Lentz constructed an unexplored geometric structure of spacetime to derive a new family of solutions to Einstein's general relativity equations called positive energy solitons. Although Lentz's solitons appear to conform to Einstein's general theory of relativity and remove the need to create negative energy, space agencies will not be building warp drives anytime soon, if ever. Part of the reason is that Lentz's positive energy warp drive requires a huge amount of energy. A 100-meter radius spacecraft would require the energy equivalent to hundreds of times of the mass of the planet Jupiter. To be practical, this requirement would have to be reduced by about 30 orders of magnitude to be on par with the output of a modern nuclear fission reactor. Lentz is currently exploring existing energy-saving schemes to see if the energy required can be reduced to a practical level. What do you think the chances are of traveling faster than the speed of light? Let us know in the comments, and please like this video if you've enjoyed it. If you want to see more videos like this one, then subscribe to Brain Impact for more. Thanks for watching.